Welcome to this lecture on polynomials. Last time we looked at Euclid's theorem, and in this lecture we look at some consequences of it. So let's recall the relevant things. So first let us recall the definition of GCD, the greatest common divisor. Fix two polynomials fx and gx over a field f, not both of which are 0. Then a monic polynomial dx is called, I say the GCD, but as far as the definition goes, we can only insist on a GCD of fx and gx. If it, first of all, is a common divisor of fx and gx. So this vertical line is just a notation for divides. So this is read as dx divides fx, and this is read as dx divides gx. So yeah, so dx is called a GCD of fx and gx if first of all it is monic and it is a common divisor of the two, and if we have any other common divisor of fx and gx, then this new common divisor is a divisor of dx. So this is the definition of a GCD, but we showed that GCD is unique. If it exists, it is unique, and we show that it exists. As long as fx and gx are not both 0, the GCD exists and is unique. So this definite article is substantiated. This is a small note that relative primality can be recasted in the terms of GCD. Fx and gx are relatively prime if and only if their GCD is 1. Alright, and Euclid's theorem states that if the GCD is dx, then there exist two polynomials, ax and bx, such that this polynomial combination, if you will, is equal to dx. So the GCD can be written in this fashion. This is Euclid's theorem, and this is the polynomial analog of the number theoretic result. Okay. So we will look at several consequences of Euclid's theorem, and this is the first one. Fix three polynomials fx, gx, and dx over a field f. Suppose that fx and dx are relatively prime and gx and dx are relatively prime. So these two are relatively prime and these two are relatively prime. Then dx is relatively prime with the product of fx and gx. Recall the analogous number theoretic result. If you have a number relatively prime to another and another number relatively prime to the same guy, then the product is also relatively prime to the same guy. That's the polynomial analog that we want to prove. So it's just a one-line argument, I believe. Let's see. So fx and dx are relatively prime. So by Euclid's theorem, we can find ax and bx such that this is equal to 1, because relative primality just means that the GCD of fx and dx is 1, and hence by Euclid's theorem we can do this. In fact, when we proved Euclid's theorem in general, we first proved it for relatively prime polynomials, and hence we are just using a special case of Euclid's theorem. Okay, so this happens for some ax and bx. I should write the full statement that because this happens, there exist ax and bx such that this happens, but let me not waste time. And similarly, there exist capital Ax and capital Bx such that this is equal to 1. So by 1 we get that, and by 2 we get that. Now just product the two equations. So this implies that this product this is equal to 1, which implies, if you do the basic algebra, this will give something like this: fx gx times some garbage, so times some garbage x plus dx times some other garbage, less ugly garbage, but garbage nonetheless. So let me say something x. This is equal to 1. So what am I saying? Just open this bracket out, multiply things. So you will get the first term as fx gx times ax. So I think the garbage, you'll get fxax times gxax. So this garbage is nothing but ax times capital AX. And what about this? Yeah, so this is the uglier garbage actually, the one that you get here. So what is that? That will be bx gxax plus ax bx fx plus dx bx capital Bx, something like that. So these two give you the first term, but the other three terms that you get when you open this bracket out, sorry about that. So the other three terms that you get when you open this bracket out will have a dx thing that you can take common, and you will be left with some ugly expression, doesn't matter what that is. So if you just look at this equation, what we have is fx gx times something plus dx times something is equal to 1. And this implies that the GCD of fx gx and dx must be 1, because as soon as you have a monic common divisor of these two, it will have to divide the LHS and hence the RHS, and hence this monic common divisor must necessarily be equal to 1. And therefore, the GCD of these two things is equal to 1, and hence these two things are relatively prime. So immediately from Euclid's theorem, the only clever step, if you will, is just to product these two equations. Okay, so that's first very important consequence. Second, suppose again we have three polynomials fx, gx, and dx over a field F, such that dx divides the product of fx and gx, and fx and dx are relatively prime. So these two things are relatively prime, but this guy divides the product of them. Then actually dx divides the second one. So this is again the polynomial analog of the corresponding number theoretic result. If you have two numbers relatively prime and the first number divides the product of the second number with the third, then the first number divides the third. And again, we will just invoke Euclid's theorem and prove it. So by Euclid's theorem and by using this and applying Euclid's theorem, we get that there exists some ax and bx such that this is equal to 1. All right. Now, if we multiply both sides by gx, so multiply both sides by gx, we get this. All right, but look at this, look at this much, the product of fx and gx. So let me shuffle things a little bit here. This ax will be written later. And by the first bullet point, by this hypothesis, this thing is divisible by dx, right? That's exactly what 1 is. So this is divisible by dx. Clearly this is divisible by dx because it is equal to dx. So the left hand side is divisible by dx and hence the right hand side. But the right hand side is dx, so we get this. Now let me not write anything. I have explained it in words. You can write the full things in your notes. Okay. This is the third important consequence, and in some sense the last one. So fix three polynomials fx, gx, and px over a field F such that fx divides px and gx divides px. So both of these two divide the third one, and assume that the two divisors are relatively prime. Then the product is also a factor of px. Again, this is the polynomial analog of the corresponding number theoretic result. So how do we prove it? Again, we will just use Euclid's theorem. So by Euclid's theorem, since fx and gx are relatively prime, we can find ax and bx such that this is equal to 1. And we want to show that the product of fx and gx divides px. So multiply both sides by px. What do we get? We get that. Okay. But let me shuffle things a little bit here. Okay. Now I'm going to write something. This guy is divisible by the product of fx and gx. Why is that? This is divisible by gx, and this is of course divisible by fx. So their product will be divisible by the product of fx and gx. Right? So the first term is divisible by fx and gx. So why is px divisible by gx? That is what is assumed. And similarly, this guy is divisible by, again, the product of fx and gx. Okay, so the left-hand side, therefore, is divisible by the product of fx and gx. And therefore, so is the right-hand side. And that is the conclusion of the theorem. So this is the third important consequence. And a generalization of it is immediately clear. This time we have n polynomials, each of which divide a given polynomial px. And assume that the polynomials, these n polynomials, they are pairwise relatively prime. So as soon as you choose two different indices, the corresponding fi's are relatively prime. And then we deduce that f1 up to fn, the product of f1 up to fn, divides px. So this is, I will leave this as an exercise, but essentially this is by induction on the previous one. Induction. But I encourage you to write down the full details. Okay, so this is all for this lecture. As usual, like, comment, share, subscribe, and I will see you next time.